Okay. Uh, so I'm going to say we're keeping kind of like, well, not say for now that I'll tell you a little bit about probability. But I will try to mention today how this talk about the short distribution is connected to the similar value composition. Why one of the reasons why I was doing it. Um, okay, and then after that, I'll explain maybe for a class, like a class or two, some of like this bracket notation, some ideas of quantum mechanics because it is connected to this thing we're doing. And then after we have all of that in place, we can do the singular value decomposition for tensors, which is, I mean, the name that is given it is like tensor trains. And after that, we can kind of like go into more applications. There should be nothing like start talking about some applications. Okay, but just to kind of like remind you, last time, kind of like what I was doing. Let's see. Oops. So I think the example that I gave you for like a joint probability distribution was this supermarket example, right? So supermarket. Or basically, there were two types of food types, right? Which were like fruits or vegetables. So two food types. Okay. And so there were two food types and there were the three potential colors, for each, So the fruits and the vegetables came in three potential colors, which were three colors, which were red, green, and purple. So again, you can kind of like introduce probability into this picture because, you know, you have like a supermarket, so you're keeping track of like what the consumer like behavior as they purchase the fruits and the vegetables. So you kind of keep tabs on what color they're buying the products. And after a long you kind of like look at the relative frequencies of how many of the items purchased were like red vegetables or red fruits or like purple fruits or whatever. And then that kind of like those frequencies, you think of like being like sort of like approximation for like the probability that a random customer would buy one of those items. So you get to this joint probability distribution, right? Which is what I had told you about last time. So you have like the joint probability distribution. Well, there's a lot of decorations that you can use here in probability theory to just like refer to these things. I'll just call it like capital P because I want to just think about it as a matrix. Okay, but I'm going to set it up as a 3 by 2 matrix. Okay, so it's going to be P11, P12, P21, P22, then P31 and P32. So here, just to kind of make sure we're all on the same page, kind of like going like the row, direction or the row axis, that's what corresponds to the color, So there were three types of color. So this is the color axis if you want. And I'm putting them in the order red, green, and purple. And and in the column direction, the column direction would be kind of like the food type. You know, if by food type you just think about whether you're buying a fruit or a vegetable. So here I'm putting first like fruits and then vegetables. Okay. So for example, what does this represent? It represents that the probability that like the customer chose a fruit which was green and things of that sort, right? So that's how you read it. Um, um, and so they're supposed to be probabilities, and kind of like almost one of the last things I was telling you, is that yeah, so each number would be non-zero between 0 and 1 actually, right? So each entry of this matrix is between 0 and 1, and then kind of like the law of total probability that you have to divide something, right? Is that if you add up all the probability, you get E equals 1. For like a silly example, just to give some numbers of like what this probability could look like. It could be something like that, right? So in that case, no one, no one bought like, for example, a purple fruit, and things of that sort. Now, let's see. I'm trying to find my matrix. Oh, there you went. Okay. Now, the idea is that when we're doing probability matrix, that's actually called as small, right? You can kind of like read off information just about each of the features, right? Like the features being either the color or the food type, right? And you can get that by adding like the elements along each row or each column, right? So that's kind of what I was telling you last time. So for example, if you kind of like add, um, if you add all these elements, right? If you do P11 plus P21 plus P31, right? So P11 plus P21 plus P31, right? Well, if you notice when you add along this column, right, what's changing? What's changing is the color of the item, right? But they're all like fruits, right? So when that, you kind of like erase the information about the color that was being, that the item had, and you only keep track of like the food type, right? Like in this case, it was like they were all chosen as fruits. So that you would interpret as, that's called like a marginal probability, and that you interpret as a probability that you would buy a fruit, So this, let's call it P of F for fruit. Okay, and so this is called like a marginal probability. And in which again, you can decorate this with more notation, but I'm not going to do that just because I'm just trying to get the idea across. And similarly, if you had like added along the second column, right? Again, you're changing the, sorry, along the second, yeah, second column, you're changing the colors. You're changing the color, so that just refers to the probability of buying a vegetable, right? And like likewise, like if you add along the rows, then you are remembering the color, but not the food type, right? So, oh, sorry, yes.
Would it be interesting if you had it across like in particular diet?
Well, the thing per se about it is that if you do that, um, you know, you're kind of like, you're combining the features, right? Like, because kind of like, you think about it as kind of like this, a color axis and a food type axis, right? So for example, if you did P11 plus P22, right? That's kind of like, it's kind of like, I mean, it would just be the probability. I mean, it has like an interpretation, right? But it would be just like the probability that purchase a red fruit or a green vegetable. Right, but like it doesn't say something about just like one of the separate features, right? Correct. It doesn't collapse if you wanted to call it that. But they do have like interpretations, right? Like the different diagonals, but not just about one of the properties. If by properties you mean color or food type, right? I want to extract something just about one of those two properties. So the diagonals for that wouldn't work, but they do work for other things, if that makes sense. And so in this case, it would be the probability of like, yeah, for a vegetable. And, kind of like by the same logic, now you are remembering the red color. So this is like the probability of red. And this is the probability. Oh, okay. I should have used actually the color schemes, but doesn't matter. And then this one would be the probability for purple. Okay. And like, I mean, it is not like a hard check. But like it's maybe better just to kind of like do it in a concrete example, right? Like, so for example, here the probability would just like of buying a fruit would have been 2/3, right? And then the probability of buying a vegetable would be 1/3. Right. So these two probabilities do add up to one, right? Because it's like a single property. So you either had to purchase a vegetable or a fruit, right? So it does make sense for the probabilities to add up to one. So these marginal probabilities are kind of like probabilities in their own right, but they are kind of like associated to like a sub property of the collective. If you think that of the collective as being like, color or food type, then it's just something about being the food type. Right? And same with the others, right? If you were to add the others like road wise, you get probability of red equals 1/3, probability of green equals 1/3, and then probability of purple would be 1/3. Right? And now the thing, you do have to be careful because the marginals per se do not determine the joint probability distribution. So it is possible for different joint probability distributions to give you the same marginals. So for example, here's another joint distribution. Where do I have it? Ah, here you are. Like let's call this 1 and 2 because they are different joint distributions. So if the probabilities had been like 1/3, 0, 1/6, 1/6, 1/6, 1/6, right? This is still like a joint probability distribution, like for the same other type, like food types. And if you do the marginals, right? If you do the marginals, this still adds up to 2/3, right? This one still adds up to 1/3, right? This one adds to 1/3. This one adds to 1/3. And the other one also adds to 1/3, right? So, so what I'm trying to say is that there's only like kind of like the independent properties. It's not enough to kind of determine the joint distribution. That's actually related to like the grant, because only if the properties were correlated, right? Like if the properties are dependent on one another, then you could count and construct the joint distribution from that separate features.
So everything has to add up to one. I mean, it's like normalized pictures.
Well, I mean, you could call it like a no. I mean, if the fact that they have to add up to one is some sort of normalization, right? It's just like, right, like there are different norms for a matrix, or ways to measure the length. And then, like, that is not the Euclidean,
I mean, I meant like, what we do for vectors, take them one.
Right. It is kind of like it's kind of like an analogous condition to being a unit vector, but you just have to be more careful because, in the case of the vectors, it's kind of like like the length if you were to draw it out. Here, if you say that that the entries have to add up to one, that is some sort of normalization. It's kind of, but it's there are different norms, so like it's not for the Euclidean one. Also, that's what I'm saying. Like if you remember, I don't know if you remember that we gave like the inner product or dot product to matrices. Like so, these are not of length one if you use that inner product. To because like the inner product is kind of like the usual one, like where you multiply the entries, so it's kind of like a sum of squares, and the squares wouldn't add up to one. That's all that I'm trying to say. But yeah, like with respect to different norm, there's an L1 norm, and then with respect to that one, you could just say that it is like of length one, but not the standard one that we were talking about earlier with the inner product. But yeah, it is kind of like similar to like being like a unit vector in some sense. Yeah.
Say more about like rank and construction of the zone distribution of probability.
Yeah, so like for example, okay, so here's like this is a fun example. So imagine like the joint, right? Let's go back to full generality, right? So if the joint distribution, I'm just going to keep it with the 2 by 3 case, just 3 by 2 case, just to make my life easier, not to put like a lot of notation, right? Okay. So let's say I tell you this matrix has rank one, right? If as a matrix, now you think about it as a matrix. So the rank of P is one, right? Okay, so we talked about this like with the tensor product construction, right? If the rank of a matrix is one, that just means that it is the sum of it is a single tensor product, right? Like that's basically what rank one means. So I'm not going to be biased, so I'll just call the vectors U and V because I don't want you to think about it, any connection with probability theory yet, right? So it's just like that is U tensor V. This is just like linear algebra, right? Like now I'm forgetting that where this came from. I just have like a matrix that just tells you that it happens to have rank one, right? So this had to be like, so again, this is a 3 by 2 matrix, right? And then, so this was like U V transpose, right? So let's just make the numbers work out. So to do this, like the vector U, I guess, has to be 3 by 1, right? So the vector U has to have like 3 entries, U1, U2, U3, and the vector V needs to have 2 entries, right? That's like playing with the sizes is always fun. So this is 3 by 1, and then when you transpose it, right, like the vector V transpose would be 1 by 2, and then yes, this just seems to be making sense. Okay, so like when you do the tensor product, right, like the tensor product in this case it was just all the possible products, right? So you multiply U1 with V1 and V2, right? So that gives you U1 V1, U1 V2, right? U2 V1, U2 V2, and then U3 V1, U3 V2. Okay, let's stop here. So far, so good. And then, for example, okay, and then okay, let's add like so that's it, and that gives you the relation between like the matrices, right? Now let's say that you add the vectors along this column, right? So that had to be, I mean, just to kind of use the same notation as before, like that was like the probability of obtaining a fruit, right? So the probability of obtaining a fruit, right, would be equal that was the marginal distribution, right? But it would also be the same that you get by adding the elements along this column, right? And then, okay, so that gives you, well, when you add them together, you can factor out a V1, right? And then you get U1 plus U2 plus U3, right? And okay, and then let's see. And then the other one was like the probability of getting a vegetable, right? The second column was the probability of getting a vegetable, right? Which would correspond now to the second column, right? And when you add the second column here, you factor out the V2, right? And then that gives you U1 plus U2 plus U3. I'm sorry, yeah.
But is it U1 plus U2 plus U3? That's just equal to one.
Well, that's what I'm trying to avoid, right? Because I'm just now thinking about this from a linear algebra perspective, right? So if from a linear algebra perspective, it's like you had a matrix, right? It happens to be rank 1, right? All of the entries of that matrix are between 0 and 1, right? But the linear algebra fact doesn't tell you that these U and B can be interpreted as probability vectors. That's what we're trying to determine whether you can do that, right? So I don't want to kind of like jump ahead. I don't want to jump like it should be forced at least to some extent by the conditions. You know what I mean? Because for example, these two numbers should add up to 1, right? If you add these two, then you get that 1, and then you add these two, then you get U1 plus U2 plus U3 times V1 plus V2, right? And then you kind of have to start playing around with the equation.
So if we solve this as like a, right, so we're given like
Right.
5 pieces of vector,
Yes.
and we have to find 6 variables.
So you're saying 5 pieces. Oh, right. You're saying 5 pieces of information because you have like the 5 marginals, right? Yeah.
But then you have another one with respect
Yeah.
or probability, the sum should be 1.
Right.
That gives you the 6.
I mean, yes.
So here we can see that they're actually linearly dependent equations because one is just.
Well, right. One, well, they like you're saying because kind of like
It's not just a multiple of the other.
one is a multiple of the other. Yeah. I mean, there's a lot of redundancy, right? Like because the matrix had rank 1, right? So there's going to be a lot of redundancy. All that I'm saying is that but you even have more constraints than that, right? Because if you look at this entry by entry, right, this number is always non-negative, and so this non-negative number is a product of these two numbers, and that forces these to either be both positive or both negative, right? So like counting the constraints. I mean, there are many constraints, right? Like it's not. So I'm just saying, like it should be. I mean, we can kind of like start it, but it should be like I'm confident, like we should be able to force, that we should start forcing that, like you can interpret these as probabilities, and then you get that it should be 0, 1 once you start adding up all that information. That's all that I'm trying to say.
Oh, so we're doing it's like say the also
if the columns are linearly, okay. If the columns are linearly dependent, you repeat that, how do you say? Okay. Right, so the columns are dependent, right? Because each rank 1, right? So none of the columns are rank 1, and then the probabilities are conditionally independent. So in the sense, you mean it like kind of like okay, so you mean like kind of like the intersection, something like this, or that's what you mean by independent, conditional independent? Yeah. I mean,
Or just place to give that. It's like you have
Oh, P of F is the same as P of F given R. Oh, okay, right, because P of F, right, because I see what you're saying, right, because if they were independent features, right, like knowing anything about the color shouldn't tell you anything about the feature, so that speaks straight to me. Yeah, like that makes sense. Yeah, yeah. No, like that is kind of like what you would expect. You don't gain any information from knowing the other, right? Like that's actually one definition of independence, right? Like two events are independent in the condition, A and B are independent in the probability of A is like the same as the probability of A intersection B, right? Because that's the same that you don't gain anything. And then if you work this out with the formula, right? That's how you get that's actually the more elegant information of like of the independence, because then you multiply both sides and that's how you get it is like factors like or multiplies. But yeah, good, yeah, so I agree with you.
No, it's gonna be.
No, I mean I think there's tons of facts. Yes, I agree that there will be tons. Yes, I'm sure we can use it. Let's try. Okay, I'm gonna an exercise. No, but it should be fun. All that I'm saying is that just to answer your question, like if you start playing with once you use this rank one, right? You have that kind of like tells you that these numbers factor into products of numbers, right? All that I'm saying is that I don't want to cheat and just say if I said already that the numbers are negative and add up to one, then it's kind of like too I'm kind of like using too much information. It should kind of like be forced by all these constraints, that we have, that the entries of the matrix are not negative, that the entries add up to one, that the columns are too marginal, that the rows are too marginal. Like there's a lot of like data. It's just like how do you play with it? You gotta just kind of like see that you could choose like these numbers to actually be interpreted as probability. That's all. But yeah, I'll try to. I mean, I have to work it out, sit down and do it myself, and then I'll put it kind of like as some sort of like hint sequence of steps so that you can kind of like see it. But I think it's like a fun thing to see that being forced. You know what I mean? But that is kind of like how. But right, like if you already because yeah, if you already knew that these are kind of like probability vectors, there's almost it could be very simple to work it out. But yeah, no, I agree that also like yeah, that's the thing. Like once you know that the variables are independent, there's a lot of like extra information that you have. So it's just kind of like playing with these like the right thing. I mean, you could make your life easier just by assuming at least a none, just make stupid cases like the none of these marginals are zero or something not like like maybe so that you can divide because for example yeah if you could divide if you knew I mean just to not make too many cases but if you assume that neither of these are zero, which seems like a simple assumption, right? That tells you that neither of these can be zero, right? And then now you can divide, and then that means that the ratio of the probabilities is the ratio of V1 divided by V2. Right, and that's how you start getting a bunch of like information about the numbers having the same sign and things of that sort. So I'm it should be possible to play with it, but yeah, I'll try to kind of like think about it like in a sequence of steps to kind of like give it out for you to work it out because it's a fun exercise. I feel like in probability theory. But yeah, that's kind of like what I want. But what just to go back to your question, what I was trying to say is that then in general, like once there are correlations between the system, like the marginals don't capture the correlations between the system, like the outcomes, because kind of like the marginals like erase information, right? Like so for example, this marginal erases like the information about the color, same as this one. And these ones erase like the information about the food type, right? So that's why you could have like different joint distributions that give you rise to the same marginals because the marginals kind of like it's kind of like killing off like information. So so you need to make extra assumptions about the joint distribution so that the marginals kind of like determine so that the marginals can actually determine the joint distribution itself, like kind of like the independence assumption. That's kind of where like the independence comes in. Were you going to ask me something?
I mean, I'm just thinking that you already have like sort of 5 equations.
Right.
And say that since this is the joint probability,
Yes.
only fair to have more.
Mhm.
So you're gonna have more equations.
Yes.
So why can't you have, given all these constraints and all these equations, and you only have 6 variables,
Right.
why doesn't this impose like very particular value?
No, I'm saying it should. I'm not saying it won't. It should. I'm just saying like you have to do it in a certain order, to not kind of like go in circles because there are too many constraints, you know what I mean? So it's kind of like how do you play with the equations in the right way to not just go around in circles because there's a lot of information that you can start using, right? And so it's kind of like, if we started just to experiment with it right now, we're going to get in a loophole. I'm sure like, trying to kind of like set it up in the right way. But yeah, I'm 100% confident that, you can just up to a scale rescaling, like, these numbers are just like the marginal distribution. That's what I'm trying to say, but like, that's kind of, this is not something that I have not said because, didn't seem too relevant. So, but, for example, if you have like, if you have a matrix that's like a rank 1, right? And you write it like this, of course you can kind of like rescale the one of, you can obviously rescale one of the vectors. You see what I mean? It kind of makes sense. Like, it's the same matrix tensor product, right? You just rescale one vector by factor t and the other one by 1/t. And since you're just multiplying the entries, then you don't see that difference, right? So, there's always some sort of like it's a minor non-uniqueness, right? It's not the end of the world, but it's still some sort of like non-uniqueness in the decomposition. So that's all that I'm trying to say. Just from the fact that it's rank 1, that doesn't obviously say that the numbers of the vectors have to be between 0 and 1, right? Because like, for example, then you could multiply each of these by -1, right? And then, so there's some ambiguities, but all that I'm saying is that you can find the correct scalar t so that, that should have like an interpretation of probability. Thanks. Okay, good. So the other thing, now I'm almost, okay, so I was trying to say like the marginal stuff. The important fact is just to kind of remember that the marginals are not enough to, in general, to reconstruct the joint distribution. That's kind of like the reason why I'm bringing it up. Now, now let me bring into the singular value decomposition. Okay. Okay, so for that, I'm going. Okay, so for the singular value decomposition, if you remember, it applies to a rectangular matrix. It doesn't have to be square. Just to kind of, actually, maybe I should remind you. So the idea is that you had a matrix A. A was a matrix, rectangular matrix. Right, and sorry, yes.
So when we know that the joint distribution is of like rank 1, don't we technically just have 5 variables, those being A1, use of 1, use of 2, use of 3, base of 1, base of 2.
Yes.
We are also given the marginal probabilities, which give us like 5 equations. So should we have like a unique solution then?
Well, I mean, the thing is like, okay, so you're thinking, okay, you start with okay, let's see. You're saying this has 6 numbers, right? But since they add up to 1, that gives you there are only 5 independent numbers, right? Like that's what you're trying to say, like, because, right.
And we know that it's just a tensor product of U and B.
Right.
We just take those U and B, have 5 variables.
Yes.
Give us the time about.
Right.
And we've been given 5 modules. So we have 5 variables.
Well, but I mean, but right, but like when you say 5 variables and 5 equations, that's not enough to say, like there's some, there can, like it depends, like because you want to know that they're generally new equations, right? Like, like that's why I'm saying, like, you cannot just count that, it is a little bit more tricky than just say you have 5 and 5, right? Because the whole point of the rank being one is that there's a lot of like redundancy in all the information, so you cannot just like kind of like um jump the gun and say, okay, this is done. You know what I mean?
Like, for example, you can represent the probability of through, it's like B2/V1 times.
Right, exactly, yeah, but right, but then kind of like
So it's redundant, and you don't really have five, so.
it is more, yeah, it's more tricky than just saying that. I mean, in fact, right, because probability of fruit probability of vegetable add up to one, so they're not like even independent. You know what I mean? Like, so yeah, it's a little bit more like there's a lot of like redundancies. All that, but I am saying that it should be possible just to kind of like make a choice, right? Make a choice that allows you to interpret the vectors U and V as probability vectors, and even as the marginals. But it does have to go through some choices. That's all that I'm. Again, I just have to work it out. I'll put it as I think it's like a fun problem. It's actually like a fun problem even in probability theory, right? In 477. So like I'll just put it like as with some hints so that you kind of go through a particular order, because otherwise you just get there's so many redundancies that you just get like in, again, like I'm just trying to avoid like a loophole where we are just going round in circles because we have so many equations, and so how do you use them? It's more like that my concern right now. So just to kind of like go back to the SVD, what I was going to tell you is that, okay, so right, if you remember, like for the SVD, what you do in the SVD is that you consider kind of like two auxiliary matrices, right? Two auxiliary matrices. Which were A transpose A and A transpose, right? So again, if you just kind of like do the count, like both are squared, right? This one I think is what is that going to be n by n, and the other one is going to be m by m, right? So they will have different sizes, right? If the matrix that you started with was rectangular, but both are square. The nice thing about them were like both were square, symmetric, as you can kind of like see, because it uses a transpose, and they had the same eigenvalues, right? And their eigenvalues were the same and non-negative. Their eigenvalues were the same. Uh, okay, so I'm going to apply the SVD, but not to the probability matrix itself, where I'm going to apply to this other one, which we kind of like this trick the other day, maybe 2 classes ago, where I told you, well, instead of working with the probability vector, or like, let's take the square roots first. So I'm going to call this like an amplitude matrix. So I'm going to apply SVD to this matrix A, which I'll call like an amplitude matrix. Its entries is just going to be the square roots of the probability of the probability. So you just imagine taking the square root of each probability, like the individual square roots. So the entry of each of these matrices, like the entry of each of these matrix squares to the probability, So like the entries of Aij is just like the square root of Pij, basically. Okay. Yes.
What is, well,
Oh, amplitude. So let's go like an probability amplitude. I mean, I'll kind of like explain the terminology more like next time. But that's kind of like the name that is given like in quantum physics to like a number that squares to a probability. So like an amplitude. Uh,
So we're constructing A from the joint distribution.
Yes, just I'm thinking is the square roots of like of all the entries, right? Which seems like kind of like weird, you know? Yeah, but I mean, that's how. We'll explain it next time that it's like a more natural construction if you understand how probabilities like the common mechanics. But I'll kind of like explain that next time. I mean, I just wanted to do it kind of like in a way that, I mean, yeah, it's kind of like weird, but at the same time, you know, the numbers are not negative, so you can take their square roots, so there might be a use in taking their square roots, right? It's not like something too crazy to try out, you know what I mean? Like, seems like the numbers are negative to begin with.
I mean, to me, it seems natural to do this, like, and then you consider. Or like a vector, the norm of the vector then means that it's like on a unit.
Well, right, that's what we did, that's how we did it for the first time on the vector, right? Yeah, when you got like a vector, a probability vector, right, if you take the square roots, right, like then you can say that it's length. It's a unit vector, right? Yeah. So I mean, yeah, I don't disagree with you, I also wouldn't find it like great, like a crazy thing to do, you know, but also you kind of have a 20/20 hindsight, you know, because you also know like how probabilities are considered in quantum mechanics. You know what I mean? Like, so it's not like a chicken and egg kind of dilemma, right? Because you already know other places where you could have like asked this, but like try to do something like this, and then it's not like a little bit of a cheat. But anyways, all I'm saying is it's not like a super crazy thing to do either, you know. And so like for example, just to kind of like show you why it's interesting to do this, like what would you have if you wanted to do like an SVD in this case, right? Like you would do A transpose A's, right? I mean, you would have to consider like the matrices A transpose A and A transpose, but let's just do like the A transpose A for now, just to kind of like show you how it's looking like. So you would do row P11, row P12. Oh, did I transpose this? No, I don't think I tried. Oh my God, like I didn't transpose, sorry. Take it back. Square root of P11, square root of P21, square root of P31. Okay, now this looks better. And then square root of P12, square root of P22, square root of P32. Okay, and then copy paste it, right? Like you paste it with, you're going to multiply it times matrix, right? So, you know, this is so good size-wise, right? Because again, this is 2×3, this is 3×2, right? So we're going to end up with a 2×2 matrix, right? Just give me a second here, just to say something. Just trying to get the right colors. Okay. Okay, so so if we have 4 entries, right? I'll just use different colors for the entries so that it's a little bit easier to keep track of them. So in the first entry would be the dot product of this vector with this vector, right? So this one times this one, it is the same number, right? So it's like the number squared, but it was in a square root. So you get P11. Then you get this one times this one. It was the same number, but it's squared, right? So the square root dies, so it's P21. And this one times this one, same thing, square root dies. Okay. And like, for example, let's do the second entry. Sorry, the fourth entry. Like, so for the fourth entry, it's kind of like the same, right? Like the numbers are the same as you do their dot product, so the square roots go away. Okay, so that's what you get in the first and fourth entry. So far, so good. Like, okay, but this is recognizable. Do you recognize? Right, like that. Okay, so this number is the sum. It's a number that we already saw. If you notice here, what you're changing, what are you changing? You're changing the I index, right? changing 1, 2, 3, but the column index is being fixed. So that is actually the sum. That's, where do I have it? That is the same as, that's the same as this one. So that's the marginal of getting the fruit, right? Like the first one, and the other one is the marginal of the vegetable. Yes.
A transport.
Right. And the other, yes, it's like, yes, it's completely kind of like same symmetric analysis, right? So if you do the other one, that along the diagonal, you get the other marginals, right. Which is kind of cool that you can just read off the marginals from the diagonals. So, but yeah, this is the probability of F of obtaining a fruit, and this is the probability of obtaining a vegetable. Okay. So along the diagonal is information, and this was 2 by 2, right? Like maybe it's useful to say this as well. You know, this is 2 by 2. And for the food type, there were only 2 possibilities, right? Like the food type only came in 2 possibilities, fruit or vegetable, right? So that kind of like would also let you know that this should give you some information about the food type. And then the other one, okay, so this like if this is going to be a symmetric matrix, right? So the off diagonal terms, they're a little bit more complicated, but they can also be interpreted in an interesting way. Okay, let's try to put them here. So if you do the other one, you'll get P11 times P12 plus root of P21 times P22 plus root of P31 P32. And it is symmetric, so it's kind of like the same number, you know, it is the same number in the third and frame. So, is that okay so far so good, everyone with me? Uh, Now, let's look at that. So I'm going to tell you that you can actually give like an interpretation to this quantity, right? So it also it's an interpretation, but it's an interpretation that actually involves more like a conditional probability. So what I'm trying to say is that when you look at this matrix, it kind of has information about the marginals, but it also has information about the interaction between the two features because it will involve conditional probabilities. So let's just kind of like, I'll kind of like switch to a more general notation, like, so the question is, let's just try to think about what this is. What is, so this quantity, like, you know, here's where like the sum notation is actually a bit more useful. So let me write it as a sum, okay? So, you know, you kind of have to identify where a sum is taking place, because if you notice, it's always 1, 2, 1, 2, 1, 2. Like, if you look at the second entries of these numbers, right, it's always 1, 2, 1, 2, 1, 2. So 1, 2, 1, 2, 1, 2, like that's fixed. Like the only thing that's being changed is like that is 1, 1, 2, 2, and 3, 3. So there's an index that's being summed over, but it's like the first index that's changing. So this is kind of like a sum from I equals 1 to 3 of, let me just emphasize it, like where the change is happening. Just to see if I have some data, right? So it's always the last two numbers, like, you know, the second entries are always, or the second numbers are always 1, 2, 1, 2, 1, 2, and then the I think, right? Okay, and then if you kind of just to kind of like, not that it's a notation that I was using before, but like the way in the order in which I called the colors X, the first color was red, the second color was green, and I told you that the third color was purple. So let me call them the colors X1, X2, X3, just to make it easier. So this is going to be purple. Okay, so this is just like the name for the colors. And the vegetables were fruit and vegetable in that order, so I'll call them Y1. So this was fruit, and Y2 was vegetable. Okay, so this sum, just to kind of like write it in a more explicit notation, this would be the sum from Y equals 1 to 3 of the probability of xi, and that's the first, that this refers to the feature fruit, so let's call it fruit. Times the probability of xi v for vegetable. Okay. So this thing, like they're kind of like, like these are the individual probabilities of the matrix, right? So like, what you're changing is the color. Okay, is the notation making sense? Yeah. I goes up to 3, right? The colors go up to 3, yes. And correct, yes, right, right. So what were your question was, like the column index, the J referred to the fruit type. Yeah. Right, so like the way I ordered them in the matrix was fruit vegetable, so the first number will be the probability of like a particular color with the fruit. And then the second number would have been the probability of the particular color with the vegetable. Okay, maybe I just, is this sum making sense?
Yeah, yeah.
Okay, so it's just like you're kind of like just thinking about how am I reinterpreting this? Or
Yeah.
because refers to the entry in row I, column 1.
Yeah.
Row I, column 1 of the matrix, right? Column 1 was the fruit column. Oh, that's what I'm trying to say.
Oh, okay, that makes sense.
Okay, good. Okay. And then I'm going to use a more, let's use the formula for conditional probability. Okay, now it's just like we're reading the formula into something that kind of like makes some sense, right? And so, okay, so now I'm going to use this formula for the conditional probability. I'll use it in the version, okay. Oh, okay, I'll use it in this version where like the probability of A. By the way, like the intersection sometimes is just written as a comma. So which is kind of what I mean here. Like I just mean like a color and the fruit, or the color and the vegetable. So like a comma, or like or like the intersection symbol, and it's kind of like this means the same in this case. So it's just kind of like. So another way to think about the formula for the conditional probability, I should erase here. I know. Right, like it's just like multiplying both sides of the equation, right? Probability of A given B, the probability of A and B, let's say, divided by the probability of B, so you multiply both sides by probability of B. And all that I'm saying is that you want to kind of go the probability theory, so sometimes comma in between. Okay. And so so that just allows you the conditional probability, just one way to think about it is allows you to replace the probability of an and or like an intersection with like a conditional probability and another probability. So these becomes a sum from I equals 1 to 3 of the probability of xi condition on being a fruit times the probability of being a fruit times the probability of xi condition on being a vegetable times the probability of being a vegetable. And the reason why I chose it this way is because then these two are not affected by the index I, right? They are constants in the sum. So you can actually take them out of the sum. Well, they come out as with the square root, sorry. You can kind of like factor them out. That's what I'm trying to say. Okay, is that so far so good? Is that making sense? Okay, and then we're almost there. The thing is that these was, I don't know if you remember, like the first time I told you about probabilities, I told you there were these measures between probabilities, distribution. So there was this, that's why I had talked there about taking the square root, right? Like you took the square root, like maybe you should go to to the notes from that day. So that must have been like kind of like maybe 2 days ago, actually. Yeah. Right, so here I was telling you about how you could measure distance between probabilities. And then here we thought, oh, maybe you could do like take the square roots of the probabilities, right? Like to get this amplitude vector, right? And one of the distances, right, as we were saying a couple minutes ago, one of the nice things about this amplitude vector is that they have length 1, like Euclidean length 1. So you could just, and then you could define a distance between the probability, just like using like the distance between the two vectors. And if you worked out a little bit, you kind of like, we worked out a little bit with the formula until we got to this nice formula with the dot product and okay, this coefficient, which was called the Bhattacharya coefficient, which was just the cosine of the angle between the two vectors, which it was literally just, I mean, oh my God, I should have put it here, but that was just the dot product between the square roots of the vectors. So this coefficient was this thing. It was just like a multiplication of like, it's not was kind of like the dot product of the square root of the probability. So actually that is kind of what's showing up here. Like, so let me just kind of like put like some notation in place. So, oops. So the idea is that, okay, so just to finish interpreting this formula, what you can do is define two amplitude vectors. So define so usually in probability theory, when you're conditioning on something, you put like kind of like a vertical line. That is what you have seen here. So one is an amplitude vector of like these conditional probabilities. But well, in square roots, right? And the other is the amplitude vector condition on being a vegetable. if you look at this, if you did the dot product between these amplitude vectors, that is literally what this corresponds to. So that is that just, and because they are, you know, they do have like length one, so like each of these has length square one, so each is a unit vector. And so the previous so basically so what I'm trying to say is that if you did a picture, oh, they are in R3, right? Because they have 3 entries. Oh, that's nice. So well, I don't know what I should call this axis, so maybe let me not call it anything. So the first vector is kind of like here. The second vector is somewhere in here. They are of length 1. So there's an angle theta between the vectors. Okay, and if you do their dot product, again, it's the product of the lengths. If you remember the definition of the dot product, it's product of the lengths times the cosine of the angle. But because each of them has like length 1, that this is just 1 times 1 times, these both are 1. So you just get the cosine of theta. Okay, and that is what we have called the big button carrier coefficient. And so essentially what I'm trying to say is that this sum becomes the sum becomes the probability of being a fruit, square root probability of fruit times probability of vegetable times this PC coefficient of these conditional probability vectors. So all that I'm trying to say is that maybe I should kind of like summarize what's going on here. Like what I'm trying to say is that the off diagonal term is kind of like measuring a distance between the conditional yeah, let me summarize in a moment what's going on. Oh, sorry, this one. Okay, so maybe let me say it this way. So there were 3 colors, right? Like the colors were red, green, and purple. Red, green, and purple, and there were 2 vegetables. So you can look at the probabilities of the colors condition of being a fruit, or the probabilities of the colors condition of being a vegetable. And that gives you 2 vectors, okay? Which are these 2 vectors that you see here. So they are probability vectors. I mean, I don't know if I said that explicitly, but when you condition on a probability, and that also satisfies the rules of a probability distribution, because that's why you scale it so that it's two to one when you condition from A is 1. So a condition of probability is a probability in its own right. So these are actually probability vectors. Like its entries are always between 0 and 1, and they add up to 1. That's what I'm trying to say. So what this is saying is that there is a distance between these probability vectors, which is being measured by, well, not the distance itself, but kind of like the overlap between these probability vectors is measured by this coefficient. And that is kind of like what shows up in the off diagonal terms. So the matrix A transpose A, just to kind of like put it like more nicely, it was a probability of being a fruit along the diagonal, you have the probability of the marginals of being a fruit or a vegetable. And in the off diagonal term, you are kind of like computing like an overlap, between the condition, kind of like an overlap between being, well, let me write it again because it's not enough space.
like the overlap between the between the two possible conditional probabilities you could have taken. Okay, that's kind of like the idea. So all that the reason why I'm saying this is that, if you look at this matrix, then it gives you not only information about the marginals, but also about the conditional probability. So it kind of like has more information than just having the margin. That's kind of the point of this construction. And same happens if you did A transpose, like, it's kind of like a similar thing, but there you would get them, maybe I'll let you work it out. But there you have like the other marginals on the columns, and then the kind of like the overlap between the different conditional. Yes.
Clarify what you mean by the overlap.
Oh, it's just that so what I had said, I think you were not here that day, but what I had said is that, okay.
How does it coefficient up front, back to the square root? That E corresponds to overlap.
No, that part is kind of like an extra term. That itself has nothing to do with the overlap. The overlap is what's inside the PC thing.
Right.
Right. Yeah, so it's kind of like, it's kind of like a rescaled version of the.
If you want to find the overlap, take those terms by square.
Right. Because you can read off the P of F and P of B from the diagonal.
Yeah.
So once you have that, you actually have their square, you kind of, these two parts can be read off. Determined by yeah. So it's not, so essentially it's the BC coefficient, because the other part can be kind of removed quite easily since you have like the diagonal information. What I was saying, right. What I had said, like the day I had talked about how to measure distances between probability distributions was like, maybe let's take out the conditional part first, without it. All that I had said is like, for example, if you had like two probability distributions, P1, P2, P3, and Q being Q1, Q2, Q3, right? Then if you look at their amplitude vectors, right, which I had called like AP and AQ, so last time, or maybe 2 times ago. Then each of these, their amplitude is a unit vector in the sense of Euclidean length, right? It has like length 1, Euclidean length 1, right? Because that, it's just like a Euclid, like, Pythagoras theorem, right? So these two are 2 unit vectors, which in this case, they live in the unit sphere, right? Like, yeah, this is actually 3-dimensional because I'm thinking of like them having like 3 coefficients. So you have like the unit sphere. Okay, you have the unit sphere, and so you have one vector being AP here, and the other vector being AQ, right? And so all that I had said is that one way to measure the distance between these probability vectors is just by measuring the distance between these 2 amplitude vectors, right? Like there's kind of like a distance between these 2 vectors that you see there, right? And then that is one form of distance called the Hellinger distance. So like the Hellinger distance was just like, the length was just the length of those, like, what is the distance between 2 points in 3 dimensions? You just subtract the entries, right? And, take the length of that. So it was just the Euclidean length of AP minus AQ, right? I think divided by square root of 2. That was a stupid normalization factor just so that it would come out to a nice formula. So divided by square root of 2, that's not too important. But then kind of what we had worked out in class, days ago, 2 classes ago, was that if you just play with this formula, that ends up being the distance squared happens to be, what was it? 1 minus the cosine of theta, I believe. Where theta is this angle. Theta is the angle between those two vectors. Okay? And these cosine of theta, so what, and this is like what I'm calling this Bhattacharya coefficient. So this is what you would call the BC coefficient of the probability vectors. So the idea is like, it's kind of like, if the amplitudes are basically very close to one another, right? So here's the thing. If these two vectors are very close to one another, right? Then their angle is almost 0, right? And so the cosine is almost 1, right? Because cosine of 0 is 1. So if the coefficient is 1 or close to 1, they're almost the same vector. So there's a lot of overlap because they're almost the same probability distribution.
It kind of shows like how related two different things are.
Well, in this case, it is your conditioning in, just to go back to the example with the supermarket, right? The two conditional, you had the colors, right? And there are two ways to condition on the colors. You can condition on being a fruit or being a vegetable. So you're comparing, how related are kind of like, it's kind of like a word salad to say it in words, but it's kind of like, of the two possible ways you could condition, how much are those probabilities related? So for example, if it was almost like if buying a fruit or a vegetable is almost indistinguishable, right? You would expect them to be very close to one another because the people don't care whether you're buying a fruit or a vegetable, right? So these probability vectors there should be a great overlap, right? If they're like a fruit and a vegetable are almost indistinguishable, but if they're kind of like almost entirely opposite things from one another, that when someone were interested in a fruit, they would never be interested in a vegetable, then you would expect them almost to be perpendicular to one another. So this is kind of like comparing, how dissimilar those conditional probabilities are about that.
Sort of anything like statistical and R factor.
Well, I don't know the R factor, but it's definitely used a lot in statistics. I have to check how they use it, but it is, yeah, but they use it. Well, the correlation, it is some sort of version of correlation coefficient, but that one doesn't involve like, I think the usual correlation formula doesn't often be curved, right? But it's not like like it's not like the same spirit, like how different, there are many ways to measure distances between probabilities. And so this is just but it's kind of like in the same spirit. Okay, let's end here because we're almost out of time. But so next time I'll kind of try to give a little bit more context to this stuff so that it doesn't look so artificial. But you'll see it's actually like a clever construction for other things we'll talk about. And I'll also have office hours, like if someone wants to stop by. But they're in my office 328, just in case. I can also stay here for a while before the next class starts.